Now we are going to find confidence interval in case of parametric distributions, where the sample basically which is drawn is not necessarily from a normal distribution, rather it can be from any other distribution as well. So here we are going to consider the case for Poisson distribution. You may consider likewise for other distributions as well. So let us begin with the confidence interval for Poisson distribution. So it is a parametric bootstrap process, okay? So from here on we are going to work with parametric bootstrap, and we are going to find confidence interval for parameter theta. So let me first import the necessary libraries. Import numpy, and from scipy.stats import Poisson. Okay, so it will import the Poisson distribution function from the scipy library, and we will also import matplotlib because we need it for the plots. Matplotlib.pyplot as plt. Now let us consider that for the known parameter, suppose your true parameter is 5. So basically here we are dealing with Poisson distribution with parameter 5. Now we are going to generate Poisson data with the known parameter. So here let me mention that np.random.seed. So this is for reproducibility, and data as Poisson.rvs. Here your mu is same as your true theta, okay, and size is 100. So this means that we are going to generate 100 random variates from a Poisson distribution with mean mu that is same as true theta. So from Poisson 5 you are going to generate a random sample of size 100. So first of all, if you remember from the theory that we are going to generate a random sample from the known distribution. Now we are going to estimate this theta, and afterwards we are going to generate the bootstrap samples, suppose say 10,000 bootstrap samples from Poisson distribution with this new estimated theta. So let us write the code for that. So first of all we will define a function to estimate theta from a sample. Okay, so what is the command? So here we are going to use define estimate, okay, estimate underscore parameter, and here we will write data. So this is the name of the function, estimate underscore parameter, and when we execute this it will return the mean, np.mean of this data. So this is a function that estimates theta. In this case the mean of the Poisson distribution will be found out and it will be used further. Now let us also specify the number of bootstrap samples that we need. So let it be 10,000. Now we are going to write the function to calculate your confidence intervals. Okay, so for this let me write define calculate underscore bootstrap. For CI let me write this. So data, estimator, and the size would be n. So here what we are doing, we are basically writing this as the name of the function, okay, and this would be the input, the data set with for which the confidence interval has to be calculated, and this function, it takes data as the input and give you mean as the output, as we have defined earlier, and n is the number of bootstrap samples that we need. So for here we are going to calculate parameter hat, theta hat, right? So here we will write, we are calling the function over here estimator data, and your bootstrap parameters, bootstrap underscore parameters, so let it be estimator. So now we are going to take bootstrap samples from Poisson distribution with this new theta hat, parameter hat, okay, and for each bootstrap sample we are going to find the mean. So we are going to apply this function that we have defined, and it will be finally stored in this bootstrap parameters. So np.random.poisson parameter underscore hat, and size would be the same as the length of the data set that you have. Right, for I, or maybe just underscore in range n. So here we are generating bootstrap samples from this Poisson distribution, Poisson with theta hat, and size would be this, and then we are applying this estimator function to each sample. Next we are going to sort them out in an ascending order, as we have done for the non-parametric case also. Sorted parameters would be found out using your np.sort function. So here we will write bootstrap underscore parameters. Okay, once you have sorted it out, you will write the command for your lower bound. So lower bound, again we have seen earlier for the non-parametric also. So sorted parameters, here we will take the integer part of this 0.025 because it is 95% confidence interval. So 2.5% of this n. Okay, so that will be your lower bound. So alpha by 2, the alpha by 2 would be left to this lower bound, and again for the upper bound, as you can see, 1 minus alpha by 2 would be there, so that basically means 97.5. So sorted parameters 0.0975 of your n. Okay, and this function would return the lower bound, upper bound, and your sorted parameters. Okay, now we will write confidence interval for theta. So here theta lower, theta upper, and your sorted parameters. So here we are calling that function to calculate the confidence interval for theta. Okay, so this one calculate bootstrap CI that we have defined earlier. So just use from here. Data, and here we will write estimate parameters, the one that we used initially, estimate parameter. So we defined it above. The same thing will be called here. So here I think I have to write the spelling parameters. E is missing. Again here. Now, sorry. Once we have calculated everything, now we can print the confidence interval, print 95% confidence interval for theta. So first of all, we will print the lower bound. So here, sorry, it will be stored in theta lower, theta underscore lower, and we are going to specify the formatting, so it will be 2f up to 2 decimal places. So again, here you will have the upper bound, and here it will be theta upper. So let us execute this. Oh, bootstrap. Even a single mistake can give you big error. So here it will be 95% confidence interval is, the lower bound is 4.51 to 4.65. So it means that you are 95% confident that when you are sampling from Poisson distribution with parameter 5, so your confidence interval would be from 4.51 to 4.65. Okay, so this is how you can see that it is easy to calculate for any other distributions as well. In theory, we learn only about normal distribution. However, in real life, you might be coming across other distributions, or maybe sometimes you do not even have an idea that from which distribution it is coming. So in such cases, non-parametric cases would be used, which we have already studied. And if you know the distribution and then you want to find the confidence interval, in such cases you can follow these steps. Okay, so I'm just showing you for the Poisson case, and here I have done for your single parameter or a single sample that you have taken. Now suppose you want to print the histogram also, as we have done for earlier cases. So let me reuse this and try to have the histogram as well, so you can see it, visualize it properly. So here let me write the correct terms. So plot, here it will be for sorted parameters. Okay, and number of bins is this. Bootstrap ratios, it will be parameter values for theta on x-axis, parameter values, frequency, bootstrap distribution of parameter theta, of parameter. Then we are going to draw a vertical line for the lower bound. So here it would be not theta, you can see we have stored it in theta lower. Okay, so you have to make these basic changes, and theta upper, sorry, it will be theta, and here you will have again, so I'm missing E every time, and sorry, here it would be 0.975, that is why it is coming incorrect. Yeah, sorry. So that is why I was wondering like why it is not covering your 95% of the histogram. So sorry for this. So it will be 0.975. Okay, by mistake I wrote an additional 0 over here. So now you can see how it covers your 95% confidence interval, and it is because you generated from Poisson with parameter 5, and here we have obtained the interval as 4.51 to 5.38. So now let us work for the case when you have to find out the confidence interval for the difference of two means. Confidence interval for difference of two means. So again we will be importing numpy as np, and from scipy dot stats import Poisson distribution, and we will also import matplotlib. So now let us set the parameters for the two Poisson distributions. Okay, so let the first theta1 can be your suppose 40, and theta2, that is the true parameter again for the second one, is 35. So the first sample will be drawn from Poisson distribution with this parameter like Poisson 40, and here it will be drawn from Poisson 35. Now we can specify the sample sizes also. So n can be, n and m both of them can be 100, and the total number of bootstrap samples, let that be 10,000. Now we are going to generate the original samples from Poisson. So here let me use data1 as Poisson. So here mu would be same as theta1, and here we can write RVS in bracket n. So we are generating basically a random sample of size 100 from Poisson theta1, that is 40. Again same way you can write for data2 also. It would be mu equal to theta2 dot RVS m. Now we will write the function to estimate the difference of means. So you will define this function estimate difference data1 data2. So this is the name of the function, that is estimate difference, and it will have this dataset, two datasets of here that we have mentioned. So for these two, confidence interval has to be calculated, and it will return the means of these two, np.mean for the first sample and subtract np.mean for the second one. So now you can write the function to calculate confidence interval for the difference of means, right? So the usual procedure is also in this way, that you have two populations, two known distributions, and from there you have taken two different samples, and using this sample data you estimate the parameters theta1 and theta2, theta1 hat, and then you are going to generate suppose 10,000 bootstrap samples from this new f theta1, and again similarly you would estimate, you will be taking bootstrap samples from this f theta2, right? You will calculate mean of each of them, and then the difference of the two means will be calculated. Now we are going to define this function for here. So define, calculate, this name of the function, calculate bootstrap underscore ci. So here data1, data2, and estimator and n, right? So again, name of the function, the two data sets with which we have to work, and this is the function that we have defined over here that takes the two data sets as the input, and then it will return the difference of their means. Now we will write bootstrap underscore differences. So we are initializing an array of zeros of size 10,000. Now for I in range, we are initiating a for loop for 10,000 times, and for each sample it would calculate. So here resample1 is np.random.choice. So we are doing sampling with replacement. So here the first data set, the size would be same as the length of the first data set, or maybe I could just write as n only, because this is what we have already defined, and replace is equal to true. It means that we are going to consider sampling with replacement. Now again resample 2 for the second one. So np.random data 2. So here the size would be m that we have defined. We can just directly write 100 also. So replace is equal to true. So for you have initiated a for loop, and for each iteration a bootstrap sample would be generated from this data 1 and data 2. With replacement it will be done, and then it will be stored these here. So I will just write an extra thing. So bootstrap differences. So what it will do, bootstrap differences. So we have initialized this. So here it would be estimator, and in bracket you will write resample1 and resample 2. So it means that this estimator function that we have defined initially, it will be applied to these two resample data sets, and the result would be stored in this bootstrap differences. After this we will sort them. So sorted differences would be here np.sort the bootstrap differences that you have found out. It's the array. Now again lower bound and upper bound has to be written. Lower bound would be so here integer 0.025 into n, okay, and upper bound here again will be sorted underscore differences, and here it would be the integer part of 0.975 into n. Okay, finally it would return your lower bound, upper bound, and the sorted differences. So finally let us write the confidence interval for the difference of the two means. So mean underscore diff for the lower one, and then it will be for mean difference for the upper bound, and you will also have the sorted differences. So this will be same as, so here it will be using and calling the function that we have defined earlier, calculate underscore bootstrap underscore ci, okay, and here it will be for data 1 comma data 2, and the sorted differences, sorry, it will not be for sorted difference, it will be for this one, estimate difference. So sorted differences will store it, estimate difference, and n. So let us see what is your mean difference for the lower one. So just not giving the entire command for this, but rather it is 0.979 and difference it is 4.32, difference of the two means. Okay, so you have obtained that 95% confidence interval for the difference of the two means would lie between 0.979 or 98 to 4.32. So it will be sorted differences here. Difference of means. Here it will be at mean underscore difference underscore lower. And this one would be the upper one. So you can see that it goes from approximately from 0.98, so you can see it's very near your 1, and it goes up till 4.32. Okay, so the difference of the two means lie between these two endpoints. So likewise you can calculate when you have your ratio of the two variances. So now let us similarly write the code for the confidence interval for difference of two, for the ratio of the two variances when the populations are Poisson distributions, okay, Poisson populations. So let me just write ratio of variances. So most of these steps would be same, with just the difference here that we are going to calculate your variance. So maybe I could quickly show you how it is done. So some steps would be definitely same, or I will copy this and we will keep, okay, let me copy till here and see what are the difference. So first of all, we are going to import the necessary libraries. Then our parameters, suppose here we can make it like 30 and 35. The size of the two samples, let them be 100 only and 10,000. And now we are going to generate a random sample from these two Poisson distributions. Once you have generated the data from the two populations, what you will do, you will define a function to estimate the ratio of variance. So let me define that function to estimate the ratio of variances. For this, define estimate underscore ratio, and here in bracket we would write data 1, data 2. Okay, and what it will return? It will return the ratio of, so it will calculate the variance for each data set and divide them, np.var for data 2. Once you have done this, now you will write the function to calculate confidence interval for ratio of the variances. So here we can probably make use of this. We will make the changes wherever necessary. So here we will write calculate boot. We are defining this function, calculate bootstrap underscore. So here data 1 and data 2 would be the input. Estimator. So basically we are calling this function that takes the two data sets and it will return the ratio of their variances. Bootstrap ratio. So let me just write, we are initializing an array of zeros over here. And for each I, a sample would be taken. And we will be doing it with replacement from the data set that we have generated from Poisson 30, and size will be 100 in each of these. And again here we will have bootstrap ratio So here ratios, it will be estimator. So we are calling this function, right? And it will return the ratio of the corresponding variance and it will be stored in this array. Now we are going to sort the ratios that we have obtained. So here also we will write, so lower bound and upper bound. So everywhere you are replacing differences by the ratios because that is the variable that you have used for storing it. Once you have obtained this, you can now finally find the confidence interval. So for this, variance, so the lower bound would be this. Let me use variance underscore ratio underscore upper, and your sorted ratios as calculate bootstrap. So probably I can use the same thing. So you calculate bootstrap, estimator, we not estimate ratio, and n. So now let us see what do you have here. It is 0.431 and let us see what is the upper bound. It is going till 0.89. So if we want to just visually see how it is working, obviously it will be a way to cross check whether the values that you have calculated is correct or not, if you have made any mistake like earlier we saw, right? So it is just a quick way to check. Sorted ratios would come over here, and here it would be not the difference of the means, but maybe you can write the ratio values, ratio of where frequency is there, bootstrap for ratio of variances. So here this will be the lower bound. You will draw a vertical line at this and a vertical line at the upper bound also. So let us run this. Yeah, so you can see that it is fine. It is covering 95% of this histogram of the ratio of the variances, and it is a bit skewed also. That actually we have seen earlier also in case of ratio of variances from your non-parametric setup also. So you can see that it is a bit skewed to the right side. So this is how you calculate the confidence interval. So with this, we complete this chapter as well as this course. I hope you learn something and gain certain knowledge about the topics of statistics. The basics that we started with the data collection, then we moved on to your summarization, visualization. Then next we studied about the sampling distribution concept, and we saw that once you understand the concept of sampling distribution, you know the distributions, then you can keep on simply applying them in further results whenever you are dealing with statistical inference, right? In confidence interval estimation, we have seen how do we reuse those results from sampling distribution. Also in hypothesis testing, we use them. So everywhere it will be used. So after that, we studied the point estimation for MLE and method of moments. We learned about unbiasedness. And in addition to that, we learn how to deal with the estimation when we have missing data, missing observations in your data set. So we learned about EM algorithm. Next, we moved to the hypothesis testing. So we studied about hypothesis testing for 3 weeks, where the first 2 weeks were about the case when you are sampling from normal distribution, and the last one is again the bootstrap case. And lastly, we learned about the confidence interval estimations, okay, both from parametric setup, that is your normal, or maybe for any other distribution, as we have seen using bootstrap, or even for the non-parametric cases also. So thank you all for joining this course. Thank you.